Hello everyone, I'm Alka Changat, your TA from IIT Kanpur, and this is your course Basics of Materials Engineering. Today we'll talk about fatigue failure theories, and this course is offered by Professor Ratnakumar from Department of Mechanical Engineering, IIT Madras. Okay, so firstly, we'll be going through some sample assignment questions, and then we'll be going through some lecture notes which will be helping you in solving assignment questions. So first question is, what decreases fatigue strength? Your options are short peening, case hardening, inclusions, and grain refinement. So we know that fatigue strength is improves when there is surface is smoother for the material. So short peening, case hardening, and grain refinement, these all help in fatigue strength. While inclusions, they reduce the smoothness of surface. So as shown here, so your surface smoothness enhances fatigue strength of a material, and inclusions, they reduce surface smoothness, and short peening, case hardening, and grain refinement, they improve tensile strength as well as fatigue strength. In case of short peening, we can see from this ascent curve as well. So for normal material compared to short peen material shows better fatigue strength, and case hardening and short peening, they introduce some compressive stresses in the surface of material, which leads to improvement in your fatigue strength. Okay, next question. Next question is, blank of material can be defined as its ability to resist fluctuating or repetitive stress. So your options are creep strength, fatigue strength, or impact strength, or tensile strength. Your answer will be fatigue strength. So in case of fatigue strength, material's resistance to repetitive stress is known as fatigue strength, while creep is a time dependent deformation for at a constant temperature and constant load, and impact strength is the resistance of material towards fracture under impact loading. So your loading will be dynamic compared to static in case of tensile strength, and tensile strength is the maximum stress material can withstand on tensile loading. Next question is, what is term referred to fatigue failure resulting from the strains caused by expansion and contraction in thermal cycling? And your options are low cycle fatigue, high cycle fatigue, corrosion fatigue, or thermal fatigue. So when there is a thermal part is present in fatigue, then it is thermal fatigue. So because of thermal gradient, there will be expansion and contraction in material leading to failure of material. So thermal fatigue occurs due to combination of thermal expansion and low thermal conductivity. So if a material has low thermal conductivity, which will lead to higher thermal gradient, and if it has high thermal expansion coefficient, that will also lead to this thermal fatigue. The strains raised is proportional to the temperature difference, and austenitic stainless steels are sensitive to thermal fatigue. Question 4 is, when fatigue occurs above blank cycles, it is called high cycle fatigue. Your options are 100, 1000, 1 lakh or 1 crore. So your answer will be 1000. So when fatigue takes place above 1000 cycles, it is referred as high cycle fatigue. And in this case, the material is subjected to lower loads, and here elastic deformation mainly takes place because it is your stress is not going above the your yield point. Fifth question is, which material don't show a fatigue limit? Your options are titanium alloys, aluminum, or stainless steel, or high strength steel. Your answer will be aluminum. So these type of your SN curves are seen in case of ferrous metals and non-ferrous metals. So for non-ferrous metals, there won't be any well-defined fatigue limit, while in case of ferrous metals, because of strain aging, they show this type of behavior. So below particular stress amplitude, your material won't fail even at infinite number of cycles. So in case of these ferrous metals, these also follow for the titanium alloys as well. So steels and titanium alloys show fatigue limits, and which means that there is a stress level below which fatigue failure don't occur, and it occurs due to the strain aging effect of interstitial atoms, and aluminium doesn't show a fatigue limit. Now question 6 is, which steel would you choose for cyclic stress application? Your options are martensitic stainless steel, ferritic stainless steel, austenitic stainless steel, or duplex steel. Your answer will be austenitic stainless steel, because this steel is FCC in structure, and so it is ductile compared to other steels, and ductile materials are less notch sensitive, so it has higher fatigue resistance, and ferritic and martensitic steels are more notch sensitive, and ductile materials are less notch sensitive compared to brittle materials, so we'll be using austenitic stainless steel. Question 7 is, the fatigue strength of a material for a life of 1000 cycles is 450 MPa, while its fatigue strength for a life of 10 to the power 6 cycles is 150 MPa. The life of a cylindrical shaft made of this material subjected to an alternating stress of 200 MPa will then be blank cycles. So for this case, you have to draw this type of graph. So we consider this to be linear. So here log S and log N. So in this case, for a particular point for 1000 cycles, here log 1000 will be your 3, and log 450, this will be 1 point, and another point will be 6, and log 150, because cycles are 10 to the power 6 cycles for your fatigue strength, and one random point is given for 200 MPa. So we have to find out what will be the number of cycles. So for this, we see that the slope of this line is same. So this, for these AB, there will be particular slope will be similar for AC. So using that, we can equate this equation. So log 450 minus log 150. So 450 minus log 150 divided by 6 minus 3. And we can equate this by saying log 200 minus log 150 minus 6 minus divided by 6 minus log n. Now we can find out the value of n, which will be number of cycles. So it will be your 1,63,842 cycles. Now 8th question is fatigue fracture consists of. Now you have to identify what will be on the surface. So there will be either cleavage, strains, striations or dimple structures. The fatigue fracture is characterized by striations. So this will be answer. So in this picture we can see that here the crack will initiate and there are beach marks and striations are seen. So this will be the answer. In case of fatigue fracture, it is characterized as striations. These are found on crack surface. These are caused by an action of tensile and cyclic stress. Question 9. So blank decrease fatigue life of a structure. Your options are round holes, smooth transitions, fillets or square holes. Your answer will be square holes. So in case of square holes, we at the corners which will act as notches and initiate cracks, leading to reduction in fatigue strength of material. So the shape of a structure greatly affects the fatigue life. Square holes can initiate cracks, while round holes, fillets and smooth transitions can improve fatigue strength compared to these square holes. Now in this graph also we can see a notched specimen always has higher fatigue strength compared to your specimens consisting notches or these square holes or these type of structures. Question 10th. What is the approximate ratio of fatigue strength to the tensile strength? Your options are 1:2 or 1:3 or 1:4 or 2:1. Answer will be 1:2. So here we can see that for steels, aluminium and ductile cast irons, it's using some research, it is measured around to be twice. Your tensile strength is twice the value of the fatigue strength. Now fatigue strength is roughly half of the tensile strength, thus the ratio is 1:2. So the factor which improves tensile strength also improves fatigue strength. That's why grain refinement will improve both tensile strength and your fatigue strength of material. Now we'll be going through some lecture notes. So there are mainly 4 theories that define fatigue. First is Orovin theory, and second is fatigue limit theory, third is Wood's theory, fourth is dislocation movement theory. So this we studied in last lecture as well, so I'm repeating this so that the concept is clear. So how the fatigue takes place. According to this theory, there are some weak regions inside material. So in some materials there can be inclusions present, or some regions which are favorably oriented to the loading axis, which will lead to their initial plastic deformation, which will make them very prone to the cracking and making this material ultimately failure through the fatigue. So according to this theory, the metal is considered to contain small weak regions along which the slip occurs easily. The metal also contains inclusions, impurities which act as notches and causes stress concentration around inclusion. And these regions are treated as plastic regions in the elastic matrix, and they experience an increase in stress even when the repeated applied stress is constant, and this increase in stress causes plastic strain in the weak region. This plastic strain increases with the increase in the applied stress on the specimen. When the plastic strain in the weak region exceeds beyond a certain value, a crack is formed. This process is repeated again and again until a large crack is formed. Now in this structure also can see if these are various grains, then this particular grain is having orientation favorable compared to the loading axis, so this will act as weak crystal. Second theory is fatigue limit theory. So according to this theory, the localized strain aging effect affects the fatigue properties to the large extent. And some metals have well-defined fatigue limits while others do not show fatigue limits. So the metals which undergo strain aging have well-defined fatigue limits, and a specimen with less amount of nitrogen and carbon will have less tendency for strain aging, and SN curve will not show any fatigue limit for this specimen. And heat treated steels, they show a definite fatigue limit. Now this is your endurance limit at which your SN curve will become horizontal. Below this, if we apply a stress below this point, then your material won't fail up to even an infinite number of cycles. Third is Wood's theory. According to this theory, there will be formation of some microscopic intrusions and extrusions which will lead to formation of crack initiation for the fatigue cracking, and these crack then further propagate and lead to failure of material. So in this case, the strain direction in fatigue is reversed again and again. So the slip produced by fatigue consists of slip bands, which are the slip movements of the order of 10 to the power minus 8 mm in length and 10 to the power minus 6 and 10 to the power minus 5 mm in height. When there is a strain in one single direction, the steps that appear are simple, and when the loading is cyclic, the simple bands tend to group as notches or ridges. The notch acts as a starting point for fatigue crack. The notch with a very small root radius acts as a stress reserve, and crack slowly propagates through the material, and after some time a stage will come when the remaining sound portion of the cross section is too small to bear the maximum load. At this point, sudden failure occurs and the final fracture is usually of cleavage type. So in this image also you can see these are the intrusions and these are extrusions. So these are the ones that will act as notch in the material. Fourth is dislocation movement theory. So in this case, the dislocations move during fatigue and consequently a localized deformation occurs in the slip bands, and the deformation is called extrusions, where some metal is expelled out of the surface. The extrusions are generally accompanied by intrusions, inverse of extrusion, and these extrusions and intrusions, these appear as early as 1/10 of the whole life of the specimen and have a height of 10 to the power minus 5 to 10 to the power minus 6 mm. These are responsible for the initiation of crack. So this dislocation movement theory is similar to Wood's theory, but it gives the what happens initial to the formation of these intrusion extrusions. Now fatigue failure is defined as the time delayed fracture under cyclic loading, and materials fail under fluctuating stresses at a stress magnitude that is lower than the even ultimate tensile strength of material and sometimes even lower than the yield strength. The magnitude of the stress causing fatigue failure decreases as the number of stress cycles increases. So this you can see in SN curve that these both have inverse relation. So either your number of failure cycles will increase or either your stress will go down. The phenomena of decreased resistance of the materials to fluctuating stresses is the main characteristic of fatigue failure. Now, examples of parts in which fatigue failures are common are transmission parts, connecting rods, gears, vehicle suspension springs, and ball bearings. The concept The concept of fatigue is used several times in this chapter, as in the growth of cracks in the Comet aircraft that led to disaster when they become large enough to propagate catastrophically as predicted by the Griffith criteria. So, fatigue, as understood by materials technologists, is a process in which damage accumulates due to the repetitive application of loads that may be well below the yield point. The process is dangerous because a single application of load would not produce any ill effects, and the conventional stress analysis might lead to assumptions of safety that does not exist at cyclic stressing. Now, in yes,
Ma'am, ma'am,
yes,
actually, I came a bit late. Can you just rewind the slides quickly so that I can take a screenshot?
okay, okay.
Yeah. Yes, ma'am. Yes, ma'am. Yes, ma'am. Yeah, okay, ma'am. Yeah, done, ma'am. Mm. Yes, ma'am. Yes. Yes, yes, ma'am.
Done.
Yeah. Ma'am, like theory, I joined from theory. You
Okay,
can, yeah.
okay, okay. I'll skip to the theory. Okay. So the fatigue process is thought to begin at an internal or surface flow where the stresses are concentrated and consist initially of shear flow along slip planes. So over a number of cycles, this slip generates intrusions and extrusions that begin to resemble a crack. So these type of flaws will generate at the surfaces of your material, which will lead to initiation of crack. Now, a true crack running inward from an region may propagate initially along one of the original slip planes, and then it eventually turns to propagate transversely to the principal normal stress. Now, when the failure surface of a fatigue specimen is examined, a region of slow crack growth is usually evident in the form of clamshell, as seen here. So, it is concentric around the location of initiation of the crack. So, the clamshell region often contains concentric beach marks at which the crack was arrested for some number of cycles before resuming its growth. Eventually, the crack may become large enough to satisfy the energy or stress intensity criteria for rapid propagation, following the previous expression for fracture mechanics. So, the final phase produces a rough surface typically of fast fracture. So, when the your size of the cross section remains very small compared to what load it can sustain. So there will be a brittle type of failure in last of your material. And in postmortem examination of failed parts, it is often possible to correlate the beach marks with specific instances of overstress and to estimate the applied stress at failure from the size of crack just before rapid propagation and fracture toughness of the material. Now, the modern study of fatigue is generally dated from a work of A. Waller, who was a technologist in the German railroad system in the mid 19th century. He was concerned by the failure of axles after various times of service at loads considerably less than expected. And a rail car axle is essentially a round beam and 4-point bending which produces compressive stress along the top surface and tensile stress along the bottom. After axle has rotated a half turn, the bottom becomes the top and vice versa. So the stresses on a particular region of material at the surface varies sinusoidally from tension to compression and back again. This is now known as fully reversed fatigue loading, which we saw earlier. Now, in case of aircrafts, but also in other structures as well, it is vital that engineers be able to predict the rate of crack growth during a load cycling, so that the part in question can be replaced or repaired before crack reaches the critical length. A great deal of experimental evidences support the view that the crack growth rate can be correlated with the cyclic variation in the stress intensity factor. But here this is the formula that is followed in this linear part of this curve. So how crack growth varies with stress intensity. So this part is given by Paris law. So this is dA upon dN, which is change in your crack length with the number of cycles. So and A and M are constants which depends on the material, and delta K is your stress intensity factor range, which is K max minus K minimum. So these parameters A and M, they depend on material. Environment can be related to your oxidation of material if it is possible, or whether it is in vacuum, your frequency of your cycling, your temperature and stress ratio. This is sometimes known as Paris law, this formula. Now this is the graph. This is how your crack growth rate changes for various materials. This type of behavior is seen. So this can change depending on various factors, but the shape of the curve remains same. So initially there will be a no crack growth, then there will be slow crack growth in this stable region. So initial steep region is there at low delta K values where no crack growth is there. Then linear region is there, which is stable crack growth. Then final steep region, which is after this linear part, it is unstable crack growth. Now this is the scientist Paul C. Paris who gave this formula. So rate of crack growth as a function of number of cycles dA upon dN, which is taken at log scale, plotted against the stress intensity factor range, which is again taken at log scale. So the plot shows a sigmoidal type of behavior divided into three regions. First region, crack initiation stretch, where your crack will initiate in this region, and in 2 your crack is propagating at a stable rate. Then third is unstable fracture, and region 2 is of the interest in predicting fatigue life. The part of the curve in region 2 is a straight line on log coordinates, and P.C. Paris defined the relationship in region 2 as dA upon dN C delta K times N. Now, fatigue crack growth life is predicted by integrating the above equation. So, Tn will be in this side. So, you can find out number of cycles that will take to fail your material depending on your crack intensity. And C and M are constants obtained through experiments. Usually M is equals to 3 for steels and ranges from 3 to 4 for aluminium alloys. Now region 1 is also interesting as it shows a threshold limit delta kth below which there is no crack propagation. So this crack propagation rates are of the order of 0.25 nanometer per cycles or less in your region 1. And region 3 is accelerated crack growth in which Kmax approaches Kc, which is the fracture toughness of material. Fatigue crack growth, so effect of increasing mean stress. So increasing the stress ratio, delta your sigma minimum divided by sigma maximum, or your K stress intensity factor K minimum divided by K maximum has a tendency to increase the crack growth rate in all regions, and the effect is of increasing R is less in region 2 than region 1 and 3, and this R is considered in this formula here. We divide this by 1 minus R Kc minus delta K, your initial equation. SN curves are well before a microstructural understanding of fatigue processes was developed. Engineers had developed empirical means of quantifying the fatigue process and designing against it. So the perhaps the most important perhaps the most important concept is the SN diagram, in which constant cyclic stress amplitude S is applied to a specimen and the number of loading cycles N until the specimen fails is determined, and millions of cycles might be required to cause failure at lower loading levels. So the abscissa and is usually plotted logarithmically. So your cycles will be on x-axis and your stress will be on y-axis. In some materials, notably ferrous alloys, the SN curve flattens out eventually so that below a certain endurance limit, failure does not occur no matter how long the loads are cycled. So the designer sizes the structure to keep the stresses below your sigma E by a suitable safety factor if your cyclic loads are to be withstood. And for some other materials such as aluminium, no endurance limit exists, and the designer must arrange for the plant lifetime of a structure to be less than the failure point on the SN curve. So here for aluminium, your graph will be like this one. So we plan its life according to particular stress that is applied and how many cycles it should withstand. So according to that, we either choose your stress, or according to stress we choose what will be the number of cycles. So the statistical variability is troublesome in fatigue testing. It is necessary to measure the lifetimes of perhaps 20 specimens at each of 10 or so load levels to define the SN curve with statistical confidence. And obtaining a full SN curve is very tedious and expensive procedure because of how many samples that are required. Now there are also safety factors that are required for SN curves. We can directly take what is on SN curve according to that number of cycles. we need to consider some safety factors. Now safety factors in stress, or this can be either in cycles. Okay, so safety factors in stress for fatigue should be similar in magnitude to other stress based safety factors such as 1.5 to 3, and safety factors in life should be relatively large as the fatigue life is very sensitive to the value of stress. So xn, which is your safety factor for life, it is in range of 5 to 20. So safety factor in life, you have to just multiply the what number of cycles that you are considering divided by the cycles that are predicted using this SN curve. And in case of stress also, you have to consider what the stress that you are using and divided by what is suggested by the SN curve. Now there are some factors that affect the fatigue strength. So fatigue strength of metal material is sensitive to various external factors including the shape and size of the part, surface finish, service conditions, while internal factors include the composition of material itself, organizational state, purity and residual stress. So stress concentration, in this case the conventional fatigue strength is measured by carefully machined smooth specimens. However, the actual mechanical parts, they inevitably have different forms of notches such as steps, keyways, threads and oil holes. So the existence of these notches, they cause stress concentration, so that the maximum actual stress at the root of the notch is much greater than the nominal stress borne by the part, and the fatigue failure of the part often starts from here. Second is size factor. So as I told earlier, if a material part is larger in size, then it has more probability of having some cracks or some defects present on the surface, which might lead to initiation of fatigue crack. So it will show lower fatigue strength. So here, due to inhomogeneity of the material structure and the existence of internal defects, the increase in the size will increase the failure probability of material, which will reduce the fatigue limit of material. And the existence of size effects is an important problem in applying the fatigue data measured by small samples in the laboratory to large scale actual parts, because it is impossible to reproduce the stress concentration and stress gradient on the actual size parts on the small samples. The laboratory results are disconnected from the fatigue failure of some specific parts. Third is surface processing state. There are always uneven machining marks on the machined surface, which are equivalent to tiny notches, causing stress concentration on the material surface, thus reducing the fatigue strength of material. The test shows that for steel and aluminium alloys, the fatigue limit of rough machining is reduced by 10 to the 20% or more than that for longitudinal fine polishing. And the higher the strength of material, it will be more sensitive to the surface finish. So these we can see as the surface roughness is reducing. As the surface roughness, there will be more fatigue life is improving. So as we keep on going for more polishing, from grinding to polishing, there will be higher fatigue life of material. Fourth is chemical composition. So there is a close relationship between fatigue strength and tensile strength of materials under certain conditions. Therefore, under certain conditions, any alloy element that can improve the tensile strength can also improve the fatigue strength of materials. And comparatively speaking, carbon is the most important factor affecting the strength of materials. However, some impurity elements which form inclusions in steel have adverse effect on fatigue strength. For example, alumina, silica.
So,
Yeah.
ma'am, like you said that these alloying elements which increase the tensile
Hmm.
strength, they will increase the fatigue strength also.
Yes.
But ma'am, like, can you just go back to the theories of fatigue, ma'am, once? I have a doubt there.
Initial theories.
Yeah, yes, ma'am. Initial theories only.
Yeah.
Yeah, ma'am. See here in Orowan theory,
Yeah.
ma'am, suppose if a carbon is forming carbide
Yeah.
and it is getting segregated along the grain boundary,
Hmm.
then ma'am that crack will start propagating from the grain boundary, right,
Yeah. Yeah.
ma'am? So like it
That's why
like
I've
won't it?
told, right, in Orowan theory, what happens? We are considering inclusions. Inclusions are not carbon, it's carbide or it's formation of some oxides or some silicates particles. Okay, so these are particles which will have different hardness compared to your matrix material. Right, as I told earlier, it will act as composite material, so there will be some interface if there.
Oh, okay, okay,
Yeah.
okay, okay, ma'am.
If
Yeah,
carbon is
yeah,
there, carbon will be in interstitial. It is improving strength. So solid solubility you must have studied, right? Solid solution. So
yeah.
it will be
Yes, ma'am.
improving
Yes, ma'am.
strength of entire material. Inclusion will also improve strength, but it is providing some interface as well. It is, yeah, that's what will be causing your weak regions in material, which can lead to formation of cracks.
Yeah, yes, ma'am.
Okay. Okay. Okay, so as it's written also here, like some impurity elements which form inclusions, such as aluminium, they can form alumina particles, and silicon can form silica particles. So these will have adverse effect on fatigue strength. In case of heat treatment and microstructure, different heat treatment conditions will result in different microstructures. Therefore, the effect of heat treatment on fatigue strength is essentially effect of microstructure. So although their same static strength can be obtained for different materials having same composition due to different heat treatment, the fatigue strength can vary in a considerable range due to different structures. At the strain strength level, the fatigue strength of a flag type of perlite is obviously lower than that of granular, because granular will have less chances of formation of notch or stress intensity. In case of graphite as well, graphite flags that will initiate your crack initiation. And the finer the cementite particle, the higher the fatigue strength. Now, in case of inclusions, they itself or they can form holes because of them. They are equivalent to tiny notches which will produce stress concentration and strain concentration under the action of alternating load and become the crack source of fatigue fracture, causing adverse effect on the fatigue properties of materials. Now, the influence of inclusions on fatigue strength depend not only on the type, nature and shape, size, quantity of inclusions, distribution of inclusions, but also on the strength level of materials and the level and the state of applied stress. Different types of inclusions have different mechanical and physical properties different physical properties and different properties from base metal and different effects on fatigue properties. For example, if there is sulfide particles, they are more deformable, so they affect your fatigue property less compared to inclusions which are brittle, such as oxides or silicates, which do great harm to the steels. Seventh is surface property change and residual stress. The influence of the, yeah, are you speaking something? Sanjeet, can you mute for
Yeah,
when
yeah,
you are
ma'am.
not
I
asking?
unmuted by mistake. Yes, yes,
Okay,
yes.
okay. So the influence of surface state also includes the change in surface mechanical properties and influence of residual stress on the fatigue strength. So the change on surface mechanical properties can be caused by the difference of surface chemical composition and structure, or by deformation strengthening. So we can roll our surface of material, and we can introduce carbon or nitrogen in the surface for improving fatigue strength of material. These are known as surface heat treatment mechanism. So surface heat treatment such as carburizing, nitriding, carbonitriding, they can not only increase the wear resistance of parts but also improve the fatigue strength of parts, especially and effective means to the improve the corrosion fatigue resistance. So the influence of surface chemical heat treatment on fatigue strength mainly depends on loading mode, carbon and nitrogen concentration in carburizing layer, surface hardness and gradient, the ratio of surface hardness to core hardness, layer depth, and size and distribution of residual compressive stress formed by surface treatment. A larger number of tests show that as long as the notch is machined first and then treated by chemical heat treatment, and the sharper the notch is, the more the fatigue strength will be improved. So the effect of surface treatment on fatigue performance is different under different loading modes, such as under axial loading, the stress in the surface layer is same as under the layer because there is no uneven distribution of stress along the layer depth. And in this case, the surface treatment can only improve the fatigue performance of surface layer because the core material is not strengthened and the improvement of the fatigue strength is limited. Under bending and torsion conditions, the stress distribution is concentrated in the surface layer, and the residual stress found by surface treatment and this additional stress are superimposed to reduce the actual stress on the surface. At the same time, due to strengthening of surface material, the fatigue strength under bending and torsion conditions can be effectively improved. Now, there are certain surface treatments that are applied to improve fatigue life. So, this is close. Fatigue life is closely related to the conditions of the surface, making surface treatments important. And treatments that produce compressed residual stress at the surface, they have a positive impact on the fatigue life and vice versa. Many widely used surface treatments may affect fatigue in different ways, which are briefly discussed here. First is electroplating. So, it is especially chromium plating. This improves your corrosion resistance of material, but and it also provides good surface finish, but it reduces the fatigue limit of steel because your type of loading, the chromium that you are plating on, it will depend on that material. Now grinding is necessary process to improve surface finish, abrade hard materials and tighten the tolerance. However, it is often introduces surface tension and the heat generated in the grinding process might damper the previously quench hardened components. Carburizing and nitriding, they produce higher strength and hardness at the surface and improves the fatigue life. Cold rolling produces a compressed residual stress layer on the surface which postpones the crack propagating from the surface and extends the fatigue life. Short peening, as I told earlier, is the process that blasts steel or glass beads onto the surface to produce residual compressed stress at the surface. It is an effective low cost treatment but leaves small dimples on the surface. Short peening can be used to partially offset the surface tension introduced by plating, decarburization, corrosion, and grinding. This short peening is mainly used for ball bearings and it is becomes less effective for low cycle fatigue components and also in case of high temperature applications because annealing type of effect will take place in that case and your residual stresses will be lost. Thermal fatigue, this is related to the structures that are subjected to cyclic thermal loadings that are likely to lead to the initiation of cracks, crack propagation and failure. Now, thermal fatigue is the gradual deterioration and eventual cracking of material by alternate heating and cooling during which free thermal expansion is partial or completely constrained. Now, if mechanical loading is also involved along with thermal loading, it is termed thermomechanical fatigue. And thermal strains induced and related to the dilation of materials lead to some mechanical strains due to clamped boundary conditions or due to structural effect from thermal gradients across the material. For example, hot zones surrounded by colder zones or vice versa. These constraints, they can be external such as bolting or welding, or they can be internal such as different thermal expansion due to different materials that are connected. The cracks may develop after many cycles of heating and cooling. Fretting and wearing, this is a surface damage resulting from the relative motion of two contact surfaces which should not move relatively. Wearing, on the other hand, is the surface damage of two contact surfaces which are designed to have relative motion. And both surface damages may range from surface pitting, deterioration, oxide debris, and cracks to functional or structural failures. Now, in case of chemical effects, they may play an important role since the surface damages may remove the protecting layers such as chromium or nickel layers that we provide to steels, and to reduce the fatigue of fretting, one may eliminate the relative motion or reduce the coefficient of friction between mating parts. To reduce this type of wearing, we can apply some lubrication and we give some precisions which will be beneficial for reducing this type of fretting. Other phenomena related to fatigue is corrosion fatigue. In this case, there will be combination of stress and corrosion. They can have a synergetic type of effect. Now, the crack grows much faster if fatigue and corrosion they coexist. It is called corrosion fatigue, and in the corrosive environment, the frequency of stress cycling influences the crack growth rate. If the crack grows sufficiently larger such that the stress intensity factor equals the fracture toughness, the failure happens in the very next tensile cycle. This condition, this can be met either by increasing the crack size or by increasing the nominal stress sufficiently. Now, in this SN curves for the different uh, corrosion, with corrosion and without corrosion, we can see that the without corrosion, it has better fatigue strength compared to when there is corrosive environment present. So your material will fail earlier if there is corrosive environment. That's all from theory. So if you have any query, you can let me know, and that's all from my side.